Welcome, folks. All right, so for a moment there, we were having some struggles with YouTube, but it seems to be willing to stream now. So we will get started. Hope that you're all well. All right, so welcome to the 24th day of remote learning. I have a really good protest joke in my collection, but I don't feel like joking about protests today. Tonight at 5 p.m., there's a rally at Victoria Park in solidarity with the people protesting the killing of Floyd George and many others. If you're concerned about the issue and want to attend, please wear a mask and keep a 2-meter distance. I know that there will be a number of Cameron students and staff there at the protest. So if you are looking for wanting to be in the general area of people you know, keep an eye out for them, and I'll be attending as well. So today's lesson is on solving trigonometric quadratic equations. We're going to take a look at 4.07.h, solving quadratic trigonometric equations. It's posted up in the classroom, and we'll work through a few of those questions. All right, there we go. All right, so taking a look at question 1, we're solving for x on the interval between 0 and 2 pi. We have sine squared x minus sine x equal to 2. The general idea is to try to think of this as a quadratic equation, and we won't always show this step. Sometimes we'll just kind of do it in our heads, but I want to show it here so that it's clear what's happening. We're going to do a change of variable. So I'm going to use u. You can use whatever variable you want. And I'm going to set it to the trig ratio that is in the equation. So in this case, if I make that substitution, I end up with u squared minus u minus 2 equal to 0. And so now you can see that we have a very typical quadratic relation here. Nothing unusual about it. It's just typical polynomial. And we can go ahead and factor that. And then let's see, minus 2, two numbers that add up to -2 or to -1 and multiply to -2 would be -2 and +1. There we go. And so we have this factorization, and we know that therefore u equals -1 from the first factor, or u equals +2 from the second factor. And at this point, we can go back and undo the substitution that we did and set the u's back to sine x's. Oops, sorry. Sine x's. And there we go. Okay. So now we need to solve both of these. Well, pretty straightforward. We're just going to follow the steps that we did last lesson. So sine looks like this. It is equal to -1 down here at 3 pi by 2. And again, we're going to be doing these all in radians. So we have 3 pi by 2. So therefore, x equals 3 pi by 2. And where does sine x equal to 2? Well, this is 1. This is -1. Up here somewhere is 2. And we know the sine graph's never going to get all the way up to there. So there are no solutions to sine x equals 2. So therefore, 3 pi by 2 is the only solution. And as always, we want to take a quick check. For this whole set of questions, we have that our angle is between 0 and 2 pi, and we allow both endpoints. So we know between 0 and 2 pi, there's only one solution for -1. There are no solutions for 2. All right, give me a 1 in the chat if that's making sense. And if you have questions, now would be a great time to ask them. And then we'll move on to the second equation there. Thank you, Caitlin. All right. So I'll keep an eye on chat. If you do have a question, feel free to ask it. Looking here at this second one, we can see it's set up exactly like a quadratic. Remember that sine squared x, that's the same thing. And I'll write it here. Sine squared x, that just means sine x all squared. It's a strange, very strange notation. And actually later in the course, you'll see that it's even weirder to use this notation than it seems right now. This is what it actually means. And so that's something important to keep in mind. Okay, so here, this is like 2 sine x all squared minus 3 times sine x plus 1 equals 0. So we could do, we use a change of variable and set u, or if you're comfortable with it, you can just leave it and think of it in terms of sine x. So I know that I'm going to have 2 factors, 2 sine x and sine x. And then I want 2 numbers that multiply, or I want to do my multiplication so that I get the -3 and the +1. So if I go -1 here and -1 here, -1 times -1 is +1. -1 times 2 sine x is -2 sine x. -1 times sine x is -1 sine x. -1 minus 2 sine x gives me -3 sine x. So we can go ahead and do the factoring this way if you're comfortable with it. If you find it tricky to do this, just go ahead and do the change of variable like we did up here, and then you can do it in a more comfortable polynomial setting. Okay, so now we can solve both of these. 2 sine x minus 1 equals 0, or sine x equal minus 1 equals 0. In this case, we'll get sine x equals 1/2. And here we'll get sine x equals 1. For sine x equals 1, there's only a single solution. That's right up here at the peak at pi by 2. For sine x equals 1/2, well, there's 2 solutions, one there and one there. We can either use special triangles or the calculator to find it. I'm going to use special triangles because I happen to remember it off the top of my head. So 30 degrees, or pi by 6 in radians, is how we get a sine of 1/2. So that means that from here at 0 to here, where that point is, that has a y value of 1/2, is going to be pi by 6 distance. And so if we think about our symmetries that we talked about last time, from this point where it's back at 0 going backwards to this point is going to also be a distance of pi by 6. And so that means if we start at here, which is pi, and we go backwards by pi by 6, that we will get to the correct answer. So pi is like 6 pi by 6 minus 1 pi by 6 is 5 pi by 6. And so then we see that there are 3 solutions: pi by 6, 5 pi by 6, pi by 2. And if you want, you're welcome to sub them in and calculate. If your calculator is not super easy to do this, like you have to retype a lot of stuff, feel free to use the website wolframalpha.com. Really good for doing any kind of computations. And you can type things in. So I can go 2 sine squared x minus 3 sine x plus 1 when x equals pi by 6. And I can just put the word evaluate in front. Wolfram Alpha knows that, or is pretty good at figuring out what the algebra that it's being asked to do is. So I'm going to give this a try, see what it says, and it gives me a result of 0. And so now if I want to go for 5 pi by 6, I can just put in a 5, hit enter. Again, I see result of 0. And if I want to do pi by 2, I just take out the 5, change the 6 to a 2, hit enter, and result is 0. So I can quickly check all 3 of my answers. And the website for that, I'll write it here and I'll also link it. It's wolframalpha.com. And it's a great place for checking a variety of mathematics. It can do most simplifications and solvings and so on. It won't show you the steps unless you have a pro account, I think, but you can at least check your answers quickly there. All right. What questions do you have about this so far? If you're feeling comfortable, give me a 1 in chat. If you have a question, let me know. Caitlin? Okay. Thank you, Ramesa. So we'll continue to work on through. I want to take a look at question 4. It's the last example that we'll do together from this page, but you're welcome to try out the others if you'd like. So question 4, we have cosine x minus 2 cosine x sine x equals 0. And you might recall that 2 cosine x times sine x is actually the sine double angle formula. So in fact, we could have written this cosine x minus sine 2x equals 0. That would have made it a little bit trickier, but we'll work from here. So the first thing to notice is I have a factor of cosine x that's a common factor. So I can common factor that out. And so now my factoring is already done. Therefore, cosine of x equals 0, or 1 minus 2 sine x equals 0. Cosine of x equals 0. Well, let's draw our diagram for that. And I like to use line paper just because it's easy to have 1, 0, -1 as your lines. So cosine starts up at 1, it goes down to 0, down to -1, back up to 0, back up to +1. In the middle here is pi. We have pi by 2, 3 pi by 2, and finally it reaches the top there at 2 pi. So where is cosine of x equal to 0? Well, right here and right here. So therefore, x equals pi by 2, or x equals 3 pi by 2. And here we get, if we rearrange this, put the 1, we get -1 divided by -2, we get sine x equals 1/2. And we've already solved that one up here. So we know that for sine x equals 1/2, x equals pi by 6, or x equals 5 pi by 6. So now we have our 3 solutions for that one. So the reason I wanted to show this one is it's okay if you have different ratios in the equation, as long as when you factor them, each factor only has a single ratio in it, we can just follow this exact same process. All right, so give me a 1 in the chat if that's making sense. Let me know what questions you have. Thank you, Caitlin. Okay, thank you, Ramesa. I'll try to keep an eye on chat. If you do have a question, please put it up. So switching back over to the handout, we're going to go to the second page now. We still have the same interval 0 less than or equal to x less than or equal to 2 pi. And now we are looking for we're looking at some more complicated equations. And so we always want to be thinking, okay, can I use some of the identities that I know in order to be able to solve this equation? So let's look at this first one here. Section B, number 1. Let me just make sure I'm, on camera. Okay. We have 2 secant squared x minus 3 plus tan x equals 0. All right. So go ahead and tell me in chat, what identities do we know that involve secant squared? Thank you, Ramesa. All right. So possibly you've got this memorized. If you don't, and you're like me, because I don't, the easy way to find it is to just go, okay, I need secant squared, so I'm going to do sine squared plus cos squared equals 1, which is the basic trig identity that you know from grade 11. I'm going to go, okay, secant is 1 over cosine. So I want to make this 1 over cos squared x. And to do that, I have to turn everything else into over cos squared x as well. And that is going to make tan squared x here, sine over cos. Cos over cos is 1. And 1 over cos, I set that up to be equal to secant squared x. So now we have the identity that Rumaisa gave us. So if you don't have it memorized, no panic. We just go, okay, we know the basic trig identity. How do we get secant? Oh, we have to divide by cos. So let's do that and see what that changes the identity to. All right, so that means that here I can go 2 times tan squared x plus 1 minus 3 plus tan x equals 0. So I'll get, doing my distributive property, 2 tan squared x. 2 times 1 is 2, minus 3 is negative 1. And I'm going to just put that at the end here. And then I'll put my tan x in the middle. So now we can see that it's set up to look like a quadratic. And we can try the factoring. We have a plus 1 here. We have a negative 1 here. Two numbers that, oh, we got the 2 going on. So 2 tan x, something, something, tan x, something, something. So if it's negative 1 here, plus 1 here, other way around. Positive 1 there, negative 1 here, then that works out. 2 tan x times tan x gives us the tan squared term. Negative 1 times 1 gives us the negative 1 term. And we're subtracting 1 tan x. We're adding 2 tan x's. 2 minus 1 is 1 tan x, and we're good. Okay, so then we can just go ahead and set each factor to 0. And tan x is a function whose range is the whole set of real numbers. All right, so sine and cosine just go from negative 1 to 1. If there's no stretch in the equation, then they're going to be very limited in what values they can take on. But tan can be anything at all. In this case, though, we don't have to worry because tan is only going to be equal to 1/2 for this one, or to -1 for this one. And so then we can use our calculator or perhaps our knowledge of the tan function or of special triangles. In this case, if we have a pi/4 angle, which is 45 degrees, that's going to be our 1/1√2 triangle. And so the tangent of pi/4 is going to be 1/1. You may recall, if we look at the graph of tangent, it's this kind of almost like a cubic graph, and it goes between two vertical asymptotes, unlike a cubic, and the vertical asymptote is at pi/2. So if we're looking for -1, that's somewhere back here, -pi/4, but we've restricted ourselves. We're only allowed solutions between 0 and 2 pi. So down here at -1, or in the negatives, doesn't work. So we need to actually look at the next branch of tan, the one that's centered around pi, where it comes down like that. And so the one we'd be looking for is here, right? Corresponding one full cycle later, the corresponding point is here. So that means instead of being pi/4 back from 0, we're pi/4 back from pi. So x equals pi minus pi/4, which is 3 pi/4. And we need to be a little bit careful here because there's actually another solution. So if we look at the next cycle of tan, it has its midpoint at 2 pi. So since we're back before that in the cycle, we're actually within the 0 to 2 pi range interval when we do this. So the other one is, or x equals 2 pi minus pi/4. And that is 8 pi/4 minus pi/4, which gives 7 pi/4. All right. So if you have questions, feel free to ask them. I'm going to go through the solving of the other half here, trying to keep an eye on the chat. So tan x equals 1/2. So that's like here, here, and here. And for that one, I think I'm just going to use the calculator. I don't think we have a nice special triangle to do it. No, okay. So tan x equals 1/2. So turn it on, make sure it's in radians as always, and then do an inverse tangent of 1/2, which is 0.5, and we get 0.46 approximately. So that's this point here. We know that one cycle later we have another one. So we can also get x equals pi plus 0.46. So if I add pi to that, in which case x is 3.61. And so we can see the calculation, here, 3.605 rounds to 3.61. So therefore, we'll clean up our conclusion here. X equals approximately 0.46, or x equals approximately 3.61, or x equals exactly 3 pi/4, or x equals, and again an exact value, 7 pi/4. So this shows you how we can use our trig identities to solve them. It shows you an example with tangent in it, and it shows you an example where we have some solutions that we don't have exact values for, but we have approximate values, and some solutions that we do have exact values for. All right. So I'm going to do one more of the questions on this second page, And I'll let you pick. So in chat, pick a number anywhere between 2 to 6. You can look at the questions and pick one that you want, or you can just pick one at random. Let me know which of the questions 2 through 6 you'd like to see done. Not seeing a lot of takers in the chat. If you do have one, let me know. But seeing no answers, I'm looking at either question 2 because it has a sine x and a cos 2x in it, or question 6 because it has tan cubed. Question 6 is really easy to factor. It's just a common factor and then a difference of squares. So let's do question 2. Question 5, suggested by Caitlin. All right, so we'll do question 5. Oh yeah, that's a nice one as well. Okay, great suggestion, Caitlin. Thank you very much. So 5, we have cotangent x times cosecant squared x equals 2 cotangent x. Okay. So a few things. One, it's tempting at this point to just divide out by cotangent x on both sides. That is kind of an obvious idea. The thing that we need to be really careful about is that whenever we divide by something involving a variable, we may be eliminating certain solutions. Because if I make this divided by cotangent x, I'm saying anywhere that cotangent x equals 0, this is not going to exist, right? Just like if you divide in a rational function, if you divide by x minus 1, the function doesn't exist at 1. So whenever we divide, we need to be careful about that. So let's take a look here. I'm going to show you what happens if we divide. What if we divide? So cotangent x equals 0 when, well, this is a bit of a weird thing, but cotangent x is 1 over tangent x. And you might be saying, okay, 1 over what equals 0? There's nothing that 1 over it equals 0. And that's kind of true, but typically actually what happens is if we get 1 over an undefined scenario, that's where we're going to get 0. And that's because if we get 1 over 0, that's undefined. And so 1 over 0 seems like it should be, okay, that's going to flip this bottom fraction and become 0 over 1. You need to be really careful whenever you're doing this kind of math. We're not going to go through all of the care needed right now, but I just want to say you don't generally just want to use this kind of argument without really checking it out and making sure you understand how it works. So the other way that we can do it, of course, is just draw a graph of cotangent 0 or cotangent x on Desmos and see where the zeros are. And it turns out that they are at pi by 2, 3 pi by 2, 5 pi by 2, etc. But these are the only ones that are within our range between 0 and 2 pi. So that means if we do cotangent x of cosecant squared x equals 2 cotangent x, and we divide both sides by cotangent x, we are immediately eliminating x equals a half and 3 pi by 2. Or sorry, x equals pi by 2 and x equals 3 pi by 2. So both of those taken off the table by doing this. We're going to need to check them later. So then we're going to get cosecant squared x equals 2. And that means 1 over sine squared x equals 2. Oh, I don't know. I may be off the camera here, so my apologies. And then if we rearrange that, we get sine x equals square root of 1/2, which is the same as 1 over root 2. And so sine x equals 1 over root 2 happens at 45 degrees. Well, we can look at our sine graph here. 1 over root 2 is going to be at pi by 4, and pi minus pi by 4, which is 3 pi by 4. So then x equals pi by 4 or 3 pi by 4. All right. So what about these values here? Well, there's two ways that we can handle it. One is we can just sub them back into the original equation and check. All right. So cotangent of pi by 2 is 0. So this term is going to be 0, and this term is going to be 0, and that's going to make the whole thing 0. So so those are actually values. So now I'm going to get some more paper. So 5 continued. Now check x equals pi by 2, 3 pi by 2. So if we sub them in, cotangent pi by 2, cosecant squared pi by 2, that's going to be 0 times, well, cosecant is 1 over sine. And at 90 degrees, or at pi by 2, sine is equal to 1. So that's 0 times 1 over 1. So that is 0. Make sure you can see it here. And then on the right side, so this is the left side. On the right side, we get 2 times cotangent of pi by 2. And that is 2 times 0, which is 0. Therefore, left side equals right side. So you can see we need to be really careful about this division process. Yes, Caitlin, I'll try and move it up a little bit here. So I'm going to talk about this part, and then I'll move the other part up. So here, when we just divided both sides by cotangent x, the simplified version of this equation is missing the solution pi by 2. So if we just do this division and we don't pay attention to which values we are eliminating, we can miss solutions. And so that's why we had to go back here and actually check those two values of pi by 2 and 3 pi by 2 to make sure that, to check whether there were solutions. And for pi by 2, we found that it is. We haven't checked 3 pi by 2 yet, but we're going to do that in a moment. All right. So be very, very cautious anytime you do a division that involves a variable. Make sure that you know under what circumstances that denominator is going to be equal to 0, and that you check whether those circumstances are actually solutions. In this case, one of them is, and I'm guessing that we will shortly find out that the other one is as well. Cotangent 3 pi by 2. Cosecant squared pi by 2. Oh, sorry, 3 pi by 2. And so that is going to give us 0 times 1 over, cosecant is the inverse of sine, so sine squared of 3 pi by 2. And sine of 3 pi by 2 is -1 Negative 1 squared is 1, so this is 0 times 1 over 1, which is, of course, just 0. And then on the right side, we have 2 times cotangent 3 pi by 2. And that is 2 times 0, which is 0. Therefore, left side equals right side. And so, in conclusion, solutions are x equals pi by 2, 3 pi by 2, or the other two that we previously found, which are these ones right here, pi by 4, 3 pi by 4. So as you can see, it can get pretty complicated. The other way that we could have done this is we could have tried using our identities to set it up. And so I'm not going to walk you through the entire thing that way, but I am going to show you just the first part. So alternative solution, use identities. So here, when we're dealing with the identities, we have to take a look. What is cosecant squared x? Well, that is 1 over sine. What is cotangent x? Well, cotangent x is cos x over sine x. And here we have 1 over sine squared x equals 2 over, cotangent. So that's going to be 2 cos x over sine x. All right. And I guess I should split these up. So this one is my left side. This one is my right side. Can I manipulate this to get something that's a little bit easier to do? And I guess, sorry, I probably don't want to split them up. I just want to subtract them. So I'm going to move this over, and then it's going to be equal to 0. All right. So at this point, I can factor out cos x over sine x. And I will get 1 over sine squared x minus 2 equals 0. And so then I might put this back to cotangent x just to have a single 1 equals 1 over sine squared x minus 2 equals 0. All right, and so now we've got it factored, and we can say, okay, well, either cotangent x equals 0 or 1 over sine squared x minus 2 equals 0. Rearrange that, we get 1 equals 2 sine squared x, or 0 equals 2 sine squared x minus 1. And we can finish solving this as difference of squares. So come back here. We will get 0 equals square root 2 sine x plus 1 times square root 2 sine x minus 1. And then we can solve each of those. equal to 0, and we'll get sine x equals -1 over root 2, or sine x equals 1 over root 2, and I'll let you finish it off from there, and you'll see that we get the same final answers that we got to the previous one if we work through this and we work through this. So hopefully that gives you a couple different ways to look at it. Like I said, please be very careful if you divide both sides. Anytime you're dividing with a variable on the bottom, there's danger that you're eliminating certain solutions. And so you need to figure out when what you're dividing by is 0, and make sure that if you are eliminating solutions, or that you check those values to ensure that you're not eliminating solutions. All right. So feel free to ask any questions that you have in the chat. If you're feeling comfortable with that and it's making sense, you can put a 1 in the chat. Up in the Google Classroom, we have a homework set. It is mostly about trig stuff, so solving trig equations, some trig modeling. There's also a little bit of solving of exponential, log, and rational equations, so you can check it out. And I would also recommend trying to do a few more of these from the handout to give them a try. All right, so I'm going to update what the homework set says here, just because I don't want to overload people. And in the meanwhile, if you have any questions, put them in the chat. And if you're feeling comfortable with that, give me a 1 in the chat so I know that we are ready to wrap up. Thank you, Ramisa. Thank you, Caitlin. All right, folks. So that's it for the stream. Give me a minute or so before you start on the homework. Just reload the page from the classroom. I'm modifying it a little bit. I think what I've given you right now is a little bit too much for one day. So I'm going to pare it down and add a couple questions from the handout as well to get you a reasonable amount there. Have a good rest of your day. See you on Friday, if not before.